Hi, we're still here in the topic integrating factor, and we have another example here. Say we have e to the x dx plus e to the x cotangent y plus 2y cosecant y dy is equal to 0. Okay, the first thing is to find where is our m and where is our n. So our m is equal to e to the x, and our n is equal to this bunch of term here, e to the x cotangent y plus 2y cosecant y. Okay, and then the next thing to do is to find the partial derivative of m with respect to y, and that is equal to since this is purely x, then this is we treat this as constant. Okay, so the derivative of constant is just 0, so we have 0. And for n, we have the term ex here, and then we've treat this as just a constant. So the derivative of the e to the x multiplied by constant, so let me write this constant cotangent y. So this is our constant, and the derivative of ex is just ex, right? So and this whole part here is purely in terms of constant and y variable alone. So this is just another constant because we only need the partial derivative of n with respect to only variable x. Okay, so this is another constant, so we have plus 0 because the derivative once again of constant is 0, so do not forget that. Okay, so we have a not exact equation here because 0 is clearly not equal to e to the x cotangent y. Then if we have done this part, then we need to find the integrating factor by let's take the subtraction of these two, and that is now equal to 0 minus ex cotangent y. Okay, so our first condition is that if this whole term here equal to n yields a purely x function, then we have to use that as an our e raised to some fx dx. Okay, so this part here is negative e to the x cotangent y all over what is our n, this whole term here. We have e to the x cotangent y plus 2y cosecant y. Okay, and then if you if you see that we have ex here, cotangent y, and ex there multiplied by cotangent y also, and if you happen to cancel that out and leave with a negative 1 all over 2y cosecant y, and that is a very big no. Okay, so if your algebra makes you think that this is right and maybe something's wrong with your algebra, you need to review your algebra. So that process is a big no. Okay, so that is very wrong. Okay, so you cannot do that. And besides, this condition here must be a the resulting function here must be a f of x or purely a function of x. But if you do this, you are a purely function of y. So maybe we can try the other condition, the g of y, wherein it is equal to the partial derivative of m minus n all over negative m. So do not forget the negative sign here. Okay, so this part here we already computed this, which is negative e to the x cotangent y all over negative our m is e to the x, e to the x. Okay, so simply you can now cancel e to the x, e to the x. So we've left with the answer cotangent y, which is clearly a purely a function of y alone. Okay, so we will now use this as our integrating factor. Okay, but my technique here to find which one is more easier to determine if I'm gonna use f of x or g of x is that I evaluate my m and n, and as you can see, I first check the subtraction of these partial derivatives m and n, which resulted to this part e to the x cotangent y, and I leave that on my mind, and I try to imagine if this part here is divided by this whole term here, and I'm trying to do some mental activity. If I do this, can I come up with a purely function of x alone? And since this is a very complicated term, then I cannot answer directly. But if I see the other part, which is e to the x, and then if I have this part here and then divided by this m, then I can easily see that I can easily cancel out the e to the x and leave with a cotangent y, which is a purely function of y alone. And from that, I can now directly use this, or maybe jump to this test or evaluation and come up with my integrating factor. Okay, to avoid this long evaluation process by having first testing my f of x, and then if this will not work, then I might proceed to the next. Okay, so my technique is just I do this numerator part here first, and then do the mental exercise, which might be can give or which might can give the purely x function alone or purely y function alone, so I can proceed directly to it. Okay, so since we have this, going back, our integrating factor now is that we have a e integral of g y dy, wherein our gy is cotangent y dy, and by having the integral of cotangent y, the integral of cotangent y is ln sine y, right? Therefore, e raised to ln sine y, we have sine y, and thus our integrating factor is equal to this one, sine y. And once again, after this step, our next thing that we must do is to multiply this with our given differential equation. So let me copy this once again. Let me copy this. Okay, we need that. Then we need to multiply our integrating factor, which is sine y. Okay, by doing that, we have a e to the x sine y dx plus e to the x cotangent y sine y plus 2y cosecant y sine y dy. Okay, so let me write first. Multiply. So let me write so that you can now follow. Multiply the given differential equation by the integrating factor. Okay. We obtain from here, we obtain this part, this new equation. Okay, and if you are confident enough to say that since we are already found the integrating factor and multiplied by our given equation, and say you are confident enough that this will yield to an exact equation, then you can now proceed to the steps in doing the exact equation. Okay, but if you are not confident enough and you might want to check if this equation is really an exact equation, then you might need to do the evaluation by equating this new partial derivative of m with respect to y and n with respect to x. The general solution is given by e to the x sine y plus y squared is equal to c. So this is now our general solution, and I am leaving it once again to you on how you can prove that this equation here is exact, and how can we arrive in this final general solution, okay, as your practice. Okay, so that's all for this video, and I hope you learned something. Thank you very much, and see you next time.